Guys, welcome back to the stream, everyone. We are gonna continue studying with what we were doing last time. I'm hella sleepy. I think it's because I woke up really early for the sake of going to a farmer's market, but as much as it was like a little bit underwhelming, like it's just typical stuff that you see at grocery stores. Maybe if I went when I was younger, I'd have been way more stoked about that because I really like that kind of thing. But yo, Assy Ace, welcome, hello, hi Jody, yo Fatima, welcome back to the stream. How's it going? How are you? I'm good. Thank you, Ace. Can I call you Ace? Yeah, I'm good. Just studying for my uh class, my only summer class. I only have one, and it's so hard to keep up with the due dates. Like, I completely forgot I have things due tomorrow, so I have to watch all the lectures for that. And yeah, it's fun when I stream while studying, just cause like, you know, I can multitask. It's not the best for studying. It's not like deep work, but it gets the thing done. Roro, what happened? What happened? I'ma go. I just wanted to come and say hi after you eat dinner. Bye, Pookies. And yeah, you can call me that. Thank you. And yeah, enjoy your food. Yeah, see you later. Peace. Hey, something went wrong. How do you feel about your mom being back? Oh, I like it. Honestly, you know, the only thing that I was like happy about while she was gone is that I thought I could have my own room, my own schedule, and at some point I did. I think the first time when she left, that's when I first started streaming, and like I made a lot of use of the days. Like I woke up right after Fajr. I'd stream at that time. I'd stream at night, and I had a whole schedule. It was really organized. This time around, like as everyone saw, I was not very organized. Even with my own space, I was just like rotting, and I was like, you know what? If I had my own room, that's what probably would have happened. But yeah, when she came back, that's when I feel like my schedule got better. Which is really ironic. I don't know what it depends on for me to be more organized as a person, but honestly, with her being back, it's much better, alhamdulillah. I think it's good with her back. I'm in Canada. Nice. Why are you in Canada, Lana? And welcome back. Honestly, it's been so long seeing you here. Oh, you have been streaming so late the past few days. I've been asleep. I know, bro. It's been a long time since I've been streaming at midnight. Not since, but like of me streaming at midnight. About 17 viewers. Yeah, that's weird. And welcome back to the stream, Nick. How's it going? In Korea. I remember you. I gotta go. Okay, no problem, Nana. See you later. Nana Basan. Or L, sorry. Bruh. Hopefully my reflection's not showing. Why is this tab here while I'm in full mode? Just put that there. Sorry. Just this thing kind of glares a lot in the morning. I don't know, and I don't want to show my reflection. So. This is so annoying. Whatever. So basically, I've noticed Toast peeing on the carpet downstairs, and I was like, huh? And then he kept doing it, and then litter box robot doesn't even record him going in the box, basically. So he pees on the carpet, but the litter robot doesn't record him going in the box. Like, are those related? Like him peeing in the box and the litter box not recording him? Is he not peeing in the litter box because of the recording? I don't know. That's so sad though. Like, the fact that he pees on the carpet, you have to clean every day. Like, that's the whole reason why Yuki gets on my nerves. Because as much as like he stopped doing his accidents, he still does it. Like, not in terms of peeing, but like stepping on his pee, coming out of that. It's my fault if I don't clean it, and I've been better at cleaning it. And he stopped that, but it's still annoying. Well, it's so hot here, like 30 degrees Celsius. Oh yeah, it's hot here too. Honestly, today's like the hottest day ever. It's 97 degrees. But randomly, it was raining. I was like, whoa. Yo, stay like funny name. Welcome to the stream. How's it going? I'm so behind on the chat. Oh, sorry. Just now I went downstairs and there's poo and pee everywhere. Oh my days. I'm so sorry, bro. You gotta clean all that. Actually, just make your husband do it. Why gay? I don't know. I'm not gay. Can I promise that? I don't know. Whatever. I promise. I promise. I don't know. I think he hasn't been going in the litter robot because he doesn't like litter. Dang, high maintenance cat. Stop spamming, bro. Username explains everything. True, the Kabir Khan. Welcome to the stream. How's it going? Assalamu alaikum. Because we changed the litter recently, but now we have to clean everything. Yeah, man. Like, how can cats be picky with what they poo on? Like, you're just gonna poo on it. You're not eating that. And most of these litters are like dust free, super bougie, and he still has a preference. Oh my days. Like, there are cats like Pixie who are really top notch. Like, they don't mind anything. You could use sand. Have you seen that meme where there's like this cat in a bag of rice and this other like bougie cat in the cat carrier and he's the one crying? It's so stupid. Like cats have so much personality. It's crazy. Can I send a link to a vid, please? No, you may not. But welcome to the stream. How's it going? I'll never get used to Fahrenheit, and when I hear Americans say things like it's 80 degrees here, I first try to process it in my head. Yeah, same with me for Celsius. I can't imagine. I just, what I do is like multiply the Celsius degrees by 2 and then add 10. And then it gets approximately to the Fahrenheit level. I wouldn't even notice that he peed, but he keeps going to the corner and digging it and smelling it. Like, bro, why are you telling on yourself? He wants to let you know. He's so proud. It's like, you like my new imaginary litter box? Wow, now it shows that there are 2 viewers on this stream. Yeah, it shows 6 for me, but sometimes it goes high and then it goes low. I don't know why that happens. But yeah, Leia, welcome back to the stream. How's it going? And sorry, player, if that's weird, or like if that made you sad. It's just like people, they link videos that are inappropriate. We don't want that. I have another question. Why are you doing homework when it's summer break? Because I have summer classes. Yeah, unfortunately. But it's not too bad. It's online. It could have been worse.
How good or how bad the model it is. We also have optimization, which can help us to gradually, make the model, good for fit the data. So here, this is a diagram of the training group. Very, very important.
Are you gonna miss Genie?
Even
I think so. I mean, it's hard not to miss a cat that you're used to already, like, everywhere. But most days, like, I don't even see my own cats. Like, I think I'll be okay. I'm not gonna miss her too much. She's really feisty and hostile, like, my dad and my mom. I don't know if my mom's gonna be happy with her gone. But, yeah, everyone's just, like, waiting for her to go. But my sister misses her the most, that's for sure. She's the most attached. Because Junie's the most attached to her. Like, that's the whole reason for attachment, is that you like each other. If she doesn't like you, like, what is there to miss? By the way, the link would send to a cool demolition video of the Stardust Hotel in Las Vegas in 2007. Oh, wow, that's very specific. If you have it on your YouTube page, I'll check it out after the stream. Oh, did she bite your dad? I think so, that's why he doesn't like her. Like, I was like, how does he know that she's hostile? Okay, oh, yeah, because he, like, tries to pick her up and she's like, maybe she did bite him. I'm pretty sure.
And the input data, X, and also the true label. So this is what we have in the training dataset. Remember, we have, this dataset. Each data item is labeled. We not only have the XI describe the data, we also have a corresponding the label or target. So given the input X, we
no problem,
Leah. We get a prediction. We will check whether this prediction is close to the given true answer. We use loss function to measure the error. So after that, we will go goes through optimization. We use gradient descent to update the weights. So here, this is our iterations. We repeat this iteration, goes through several times until the weights can enhance a regression to learn the good value of those weights so that it can, now each house, we have two features. Um,
I'm getting PTSD from the lecture's accent. It's so hard to understand. Yeah, bro. Even the captions are wrong sometimes.
the number of the weights we have or the number of parameters we have are three. The loss function we use still MSE, so we will check the prediction. So this one is prediction. Whenever you have X, you put into this linear combination model, you get prediction. That we check the differences between the two answers and the prediction. We're still doing square here because we care the magnitude, right? After that, we get the overall error.
I gotta go clean poopy bye. I'm excited to see you this Saturday, inshallah. This Saturday? Whoa, that's actually so close. Like, that's in 6 days. No way. Okay. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh. Have fun cleaning your poopy. And pee pee. Don't forget the pee pee. That corner. But yeah, see you this Saturday, inshallah. Take care.
Among the given data set. So this is the loss function. We call this is MSE, mean square error. After that, we're doing gradient descent in optimization. So suppose we're starting from random weight values. We follow so here this is gradient, but we follow the negative gradient direction. This one is a learning rate. So this is the computation carried out by one iteration. We go through many times until we get good value. So on the right here, this shows.
Hi, Johanny Castillo. How's it going? Do you remember me? I do. You're from Texas. I don't know why. That's the only thing I remember. I don't know if I'm right even, but welcome back. You're the green one in your profile picture. And Nick, what is that reaction?
It's a vector of partial derivative of this loss function with respect to each parameter, right? So here, this should be there's a one missing here. We also have the third one, right? Because we have three parameters. So the gradient is like we handle. So now how can we use matrix to represent it? So here, suppose we download the data. This is X of each data base in linear combination. We can have this W0. Okay. So now let's evolve to after let's make it general. Suppose this is the form. So this is a way use.
What are you watching? I'm watching some lectures of summer classes. I'm studying right now, but if you are studying too, you can study alongside, or like tell me about your day because studying is boring. So.
The matrix to represent it. So on the left, this should rewrite each item explicitly. But in practice, as mentioned, so for example, here this is element W is the characteristic to function. We have iterations right to carry out. However, taking the gradient equals 0, right? So you can get a status processing solution. This method which was not used in the training as new data, right? As shown here in orange.
Sorry for skipping so much. Like y'all could learn too, but like I kind of did this already. I forgot where I stopped at, so I'm just watching.
So those new data was not used before in the training, and we use this new data to check the performance. Okay, so we call this is a kind of a testing data set or validation data set. So
datasets and machine learning, training dataset, and validation dataset. Important, we'll discuss that soon. And testing dataset. Okay, so there's 3 types. I forgot what was writing here. Predict how generalizations. Models' ability to predict new data. So there's training, there's testing, and there's validation data set.
But we will later talk about the validation data set very soon. Um, so for here, just keep in mind, you use some, you use data set to train.
I wonder if when Americans speak subtitles appear below them, or is it only on TikTok? No, like there's subtitles here too. It's not just TikTok. It's like a caption for like, yeah, I don't know why there's two C's in it, but yeah. It's helpful when there's like somebody who has an accent, like you can't really tell what they're saying. Even when somebody's speaking with an English accent, it's like sometimes you can't really tell what they're saying either. Like I can't watch movies without subtitles. I just prefer that. Normally I wouldn't, but like my mom likes it. But then I got used to it too. I'm like, where's the captions?
The model, but you also need to prepare another data set or another model, one or two data set, which can help you to check the performance. Why? Because we care generalization in machine learning. If the model only good for the training data set, that's not the point that we want to get. And we want to see how good this model.
So we need both of them basically, training and testing, because just testing data points won't give you the best model.
Well, it is one year.
I'll never be able to understand English by ear like native speakers because this damn world adds subtitles everywhere. So you want to do it without subtitles? You want to be able to learn English by ear? I know that's the thing though. Like artificial intelligence and subtitles and all these technical stuff. It's helpful, but at the same time, it's ruining our own brains. Like it's impossible to learn nowadays on your own. You know, at least for me. From my personal experience, like what's it called? Doing stuff like for my brain, impossible. If the ability to do it using AI exists, I'm gonna use AI. I'm gonna take the shortcut. Our brains are made to take shortcuts. Like that's how it works to make life easier. But yeah, that's what reduces the gray matter in our brain. Like you can't actively increase your gray matter like it's, I don't know, like a painting or something. But doing hard things makes your brain more powerful. Like you rely on yourself, your own powers. And that's what makes people dumb, is that they don't do hard things anymore. And me included. I would have learned how to code perfectly by now with all my coding classes, but since AI can do a lot, it's not helpful. I think it's mainly a problem with the English language since it has so many accents. Yeah, I guess it depends. Like even in America, like there's a different accent everywhere you go. There's like Southern accent. There's the Californian accent. Mine right now, I think that's Californian. And then there's New York accent. It's everywhere.
Handle
And there's British. That's not American either, but.
Right. Um, so another one for here, we learned the linear regression model. Right, linear regression model, is just based on the linear combination. For example, let's say suppose we have one single feature, right? And this one is the predicted value. This is just a single line, a linear line in this 2D space. If you treat x as that feature axis, y is the predict value. When you handle two features, two variables, and we know now the space is a 3D, right? So this linear combination represents a linear line, a linear plan in the 3D. When you have more models, it's just a hyperplane in the higher dimension space. So this.
So that's what hyperplane is. It's just a higher dimensional space. You can't really picture that. You could only picture like 2Ds and 3Ds, but 4D, 5D. So hyperplane. Linear regression models we learned. It's A subspace of one dimension less than its space. When I chat with Indians online in English, sometimes I feel like they're speaking an otherworldly language, but I'm starting to understand them. I mean, chat in voices. Yeah, that's how other languages work. Like, it sounds otherworldly. It's like, what dimension am I in? It's really weird, but it's learnable. That's what we believe in our religion, is that God created different tribes so that you could get to know them, so that you could learn new languages, and like it's good for your brain too to learn multiple languages, being a polyglot, and yeah, you get to connect people with people and learn about their culture and see how they thrived in their circumstances. It's really interesting. Like I think if I were more extroverted or able to afford traveling and connecting to people, that'd be such an ideal life. And that's how people used to live back in the days. They had to travel, they had to, you know, go around the world. But nowadays it's just impossible. I feel like I think it was possible if you really wanted it. If you really want it, but yeah, living cost is pretty bad. We'll see, inshallah. Allow us to travel. And welcome, King and Queen. Welcome back. How's it going? I'll forbid math and learning. That's, actually, that was my wish as a kid too. But the older you get, the more you realize math is not the enemy. It's the grading that's the enemy. It's the failures, the shaming, the negative feelings. If you really learn math and hard things, it helps your brain, the gray matter increase. You're better at decision making. You're better at concentrating, focusing, all these things. Like math is really good for you. I'm in the car again, so I can't hear you. I'm heading to school. Okay, have a good day at school, Queen. So, one variable gives you this. Yx equals the weight plus the weight times the variable. Weight 1, x1. And it looks like this. It has 2D, 1 data points, and there's two variables. And that looks like pretty much the same thing, except there are two variables, and then we got that three-dimensional space like that. This is the x, this is the y, this is the z, and then yeah. It's 8 degrees Celsius, and I'm so cold. Dang. That does sound really cold, even though I don't know Celsius, but I'm assuming that's around, let's see, 26 degrees Fahrenheit? Someone correct me on that. Am I right, guys? So we have WO plus W1 X1 plus W2 X2 dot 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 X WN XN. And we don't know what that looks like, but that is a hyperplane. These are just different types of hyperplanes.
Linear line or linear plane in the 3D. When you have more models, it's just a hyperplane in the higher dimension space. So this is the linear. But now, how do we know this linear model is really good or not, right?
What if our linear model is not good for the data to write? What if the linear model is not good for this data? We can use a more complicated model, polynomial. Wow, okay, so just like one line won't capture anything. But the fact that there is still a shape here, you could use like x squared, right? That's a polynomial, to get that kind of graph, or like I don't think that's x squared. It has like an x squared in the equation, but it looks kind of like a sine, right? That is 46.6 in Fahrenheit. Okay, yeah, I was far off. How do you calculate Celsius to Fahrenheit? I definitely did this in a lab before. Let's see. How to calculate Celsius to Fahrenheit. So easily double the Celsius number and add 30. Oh, I doubled it and added 10. Okay, so adding 30 is how you calculate. Wow. Wow, it's pretty close. Nice. I did that for a coding problem. So many. Anyways, so if our linear model is not good, we could use a more complicated model, polynomial. Okay, I gotta go. Bye. Bye. Take care, Queen, and have a good day at school. See you later. Thanks for teaching me how to convert.
Okay. So can we, if it is not good, for example, those sample data points actually they are, sampled from some cosine or sine function.
Yeah, sine
We
function.
know definitely the linear model, especially for example, this 2D line is not good enough to feed those data. Can we use more complicated data in linear regression to feed or to find to represent a curve rather than a single line to feed the data? Of course we can. So here we will show you an example. But the key thing is we can use this example to explain overfitting. Okay? So what model we can use? Let's
Overfit. Linear regression with one variable. Linear regression with multiple variables. Generalization with supervised learning. And key concept. Linear regression using polynomial. So these are linear models for regression. Key question. Okay.
But the key thing is we can use this example to explain overfitting. Okay?
Overfitting. Okay.
So what model we can use? Let's use a polynomial. So polynomial is just the sum of the powers, right? And each power term.
An nth order polynomial function of one-dimensional feature x, where x of j is the jth power of x to the power of j. Nth order polynomial function. Okay. Let's see what he means.
So we have the corresponding coefficient. So here, let's say this is our machine learning model representation. So suppose, let's say we only have a single feature. So here, this is a single feature. Okay? Instead of only consider W0 plus W1x, right? This is one linear combination model, maybe too simple. What are we going to use? We use W0, W1, x, W2, x2. We use this polynomial based on the powers of the feature. Right? Of course, the more, the higher the degree of the power terms we have, the more general this model will be, right? And it no longer may with the power items with degree greater than 2, it no longer represent a line, it represent a curve, right? For example, here, if you choose this n, suppose you consider W3x power 3, so this term, so this represents, this line, the right line. Okay. So now let's try to figure out those parameters W. So we hope this model line can fit the data the best.
How do you even take notes of that? Like everything he just said.
suppose, let's say we only have data. Okay? So what model we can use? Let's use a polynomial. So polynomial is just the sum of the powers, right? And each power term.
So polynomial is the sum of the powers. I visit the 24/7 7-Eleven under my apartment almost every day and buy the same rice, meat, and kimchi meal set. The owner sees me so often that today he asked the usual. Aw, that's cute. That he recognizes you and yeah. That's good though. Like, that's the one. I think I already mentioned that from a previous conversation or on a live stream. Is that the convenience stores are something that attracts a lot of tourists like me. Like, I would have, if I go to Korea, that's the one thing I'd want to try the most. Too bad most of them are not halal though. Like, I would obviously get shrimp and like tuna, that type of thing, seafood, because that's like the only thing that we can eat that doesn't have to be slaughtered by humans. I mean, Muslims. Oh, sorry.
We have the corresponding coefficient. So here, let's say this is our machine learning model, right?
Okay. X and W equals the weight plus the polynomial here. J equals 1, WJ, X. Polynomial function of one-dimensional feature X. In nth order, polynomial function of one-dimensional feature X. In Russian-speaking areas, halal food is common because there's a high concentration of migrants from Muslim-majority countries like Uzbekistan. Ooh, nice. And I would expect like Dagestan, right? Dagestan is part of Russia, or is that another place? Is that like a city or a country? I think it's a city in Russia, right? I'm not sure. Correct me though.
So suppose, let's say we only have a single feature. So here this is a single feature. Instead of only consider W0 plus W1x, right? This is one linear combination model, maybe too simple. What we're going to use, we use W0, W1, X, W2, X2. We use this polynomial based on the powers of the feature. Of course, the more the higher the degree of the power terms we have, the more general this model will be. And it no longer make the power items is degree greater than 2. It no longer represent 1, it represents 2. For example, here, if you choose this n, you're supposed to consider W3x power 3. So this represents, this line, the right line. Okay. So now let's
Powers represent curves, not lengths.
trying to figure out those parameters W. So we hope this model line can fit the data the best.
So these are parameters. The weights. Dagestan is a sovereign republic constituent entity within the Russian Federation. Okay, so it's part of Russia. It's not a city. Okay, okay. That's cool though. It's not a city, but it's like a part of Russia. Hmm. So, what is it then? It's like, what is a sovereign republic constituent entity?
Right. Now let's yeah. So actually for here, in it, you can think about, so although suppose we only consider a single feature, but because we consider the powers, you can think about now this is a linear regression problem with multiple variables, multiple features, rather than one. Why? Because although we just have one feature, but we power it, so you can think of this is additional human created figures. So that's why each item we can give, we can give the weights to associate it to train in this machine learning process. Okay, so now let's talk about the overfitting. So for given
I didn't understand what he said here. This is a linear regression problem.
with multiple variables, multiple features, rather than one. Why?
Okay, so it has to be multiple rather than one.
Because although we just have one feature, but we power it, so you can think of this is additional.
Okay, so powers equals multiple variable problem.
Net, you can think about, so although suppose we only consider a single feature, but because we consider the powers,
Polynomial models are multiple variables even with one feature. I have awake. Yo, Kobe, the Cup 8000, welcome to the stream. Good morning, I guess. What time did you wake up? What can we possibly be talking about? uh, Dagestan. Hi, Assalamualaikum. Imagine if Native Americans had their own autonomous state, so that's Dagestan. Oh, yeah. Except the Native Americans here in America do have their own place. It's just really, really poorly taken care of. It's like the worst nutrition scale people. I don't know how to word it, but like they have the worst care in the whole state, the whole country. It's so sad that they treat Native Americans that way. We have many ethnic republics, which are regions with their own cultural identity, languages and traditions within the country. Oh, okay, okay. Ethnic republics. That makes sense. Russia is really cool, bro. Like, they care about everyone. Are you man or boy? What do you think? Which one?
you can think of now this is a linear regression problem with multiple
Multiple variable linear regression problem. I don't have an eraser. What I miss and wow. I'm from one of the ethnic republics. I'm basically a native Siberian and half Korean. Oh, I thought you were fully Korean, just born in Russia. That's cool. You're native Siberian. I wonder what that looks like. Banana pepper. I'm a manner girl. Banana pepper. I think I'll go with that. I think I'm a banana pepper.
variables, multiple features, rather than one. Why? Because although we just have one feature, but we power it, so you can think of this is additional human created features. So that's why each item we can give the weights to associate it to train in this machine learning process. Right. So now let's talk about the overfitting.
Regularization.
To associate it to train in this machine learning process.
So linear regression continuous outputs. Simplest model, a linear combination of features. Key concept is supervised learning, unsupervised learning. Loss function. Did I write that down? I wrote gradient linear model and loss function. Let's see. I know you was a banana pepper. Wow, how do you know? That's crazy. Where do you get this slide from? I feel like I should write that down. Fit to unseen tab. I feel like I already wrote it though. I can't see anything in this. Ah, see? I did write it down. Alright, let's continue. I'm a math teacher and my brain is starting to hurt. You are? That's crazy. What do you teach?
Right. So now let's talk about the overfitting.
Let's use polynomial model to explain overfitting. Okay. The data is generated from sine 2 pi x with small noises. Okay. Let's write that down. Just for the example. This is negative 1, 0, and 1. We have the dots going in that sine function, stuff like that. And we got the line. What do I teach algebra 1? Nice.
So, for given...
I love algebra 1. That was so fun, bro. I wish I could also teach algebra 1. Do you get paid a lot? Like, is that your, like, permanent job or just, like, your current job? Are you planning to get, like, a better job? This tab is so annoying. I'm trying to exit, but it's just telling me to X all my things. Like, I gotta use my system. Your system has run out of application memory. That's crazy. Oh, no.
Let's check different models using, suppose given the n. For example, the n equals 0. We know when m equals 0, this model is too simple. So
M is, what was M again? Mth order polynomial function. Let's see. When m equals 0, the model becomes too simple. Forever. I've been there for like 20 years. Really? Like, how much do you get paid? Because that seems like an easy job. Like, if you're good at the subject and you teach it, I feel like I could do that every day and not get bored. It could be annoying though if the students are bad. But I think it's really gratifying when you see somebody go from not understanding anything and then learning it in front of your eyes. Like, oh, that's how it works. 100 every year. Wow.
Suppose
You're not answering the question. Oh, you get 100 every year? Is that your salary? 100K?
or zero here, that means we no longer have this power. We just have this constant term. So that's why no matter what x the value it is, the y prediction will be always the same. So that's why it only can represent a horizontal line there.
Only represents horizontal line. Because y x w equals w0 plus and j equals 1 wj xj. Only counts the way. I forgot you was here. What? Oh yeah, Nick. Native Siberians often share similarities with Mongols and Chinese. My ethnic group is closest to Mongols, so in simple terms, I'm half Mongolian and half Korean. Yum! Cause Mongolian beef, sorry. That was bad. But yeah. Mongols, that's crazy though, cause you know how Uzbekistan was, you know, taken over by Mongols. Like I heard about the genocide. Like it was so sad. But what else? So like you're Russian, but like Mongolian Russian. That's crazy. I'm eating beef jerky. Nice, and welcome back to the stream, Catherine. How's it going? I was late too. You're 47 minutes late, but it's fine. We're not even halfway through this lecture. I feel like it's gonna be a long stream. Unless I stop over here somewhere, like 20 minutes later, because I'm getting kind of hungry. I should probably eat something. Some indigenous Siberian peoples share ancient ancestry with native Alaskans due to ancient migrations across the Bering Land Bridge. Whoa! What is the Bering Land Bridge? That's so cool. Alaskans, huh? What do native Alaskans look like? Indigenous people. Oh, wow. What did you say? The Bering Land Bridge. What does it look like though? Doing two brief windows. Oh wow, that's so cool. And why is everything blurry? Subhanallah. So it goes from Alaska all the way to Russia. Wait, I didn't know Alaska was that big though. Bruh. Makes sense though, that's crazy. Welcome back. I wasn't here. I mean, welcome back from previous lives, that's all. Because you're not a new member, right? Yes, but since I look Korean and have a Korean surname, I usually just tell people I'm Russian Korean. Okay, so you look Korean. That's good. If you look too different, like a Russian completely, then you'd probably get like looks and stuff, or like be like an oddball in society. I'm cashed out. I just need to leave my job. Really? How do you catch that? I thought teachers don't get paid that good. And why would you want to leave it though? I kind of want to be a teacher, honestly, which is bad because teachers don't get any respect.
So now suppose you check the arrow, right? Suppose you check here, this one, and this one. So now you check the differences between the predict and the true value. You definitely get a really high, the error in prediction. As mentioned here, we have a training and we have testing. As well. Okay, we also have some. We also have a separate the data items which form a testing data set, right? Which the model with those data sets was not uh, used to train the model, right? We just want to use it, not just separate unseen new data. We want to check the performance. That's it. So that's why, because this model is too simple, right? Definitely cannot fit the data well, so we get a really high model. The error. Now let's improve the model by using the power terms. So suppose m equal 1. M equal 1, this one is kind of like the linear line. Like,
So adding another weight would help make the model have less errors. The next one is where get the worst, the most dangerous human being ever. Where get the what? What does that mean, Kobe? Next one is where get the worst, most dangerous human being ever. That's Netanyahu, hands down. So because only one weight has such a high error, we need to consider more. More weights. So that goes like WO plus W1X1. Those kind of linear combinations. FYI, the Bering Strait Ice Bridge theory of North America native migration is largely discounted by scientists. It was pseudoscience based on assumptions those people weren't smart enough to build good boats. That's crazy. I mean, the pictures showed it was like probable, but I guess it could be pseudoscience. I don't really care though, because, that doesn't really change my life. But yeah, thanks for clarifying that. Reese P. And how's it going? Your name reminds me of Reese's Pieces, like the Reese's like cereal. Man, I kind of want that now. I'm getting pretty hungry. Like, so we've been studying for 53 minutes, right? Where does this guy come from? I don't know, man. That is. Yep, I get that a lot. Really nice. Beef jerky is so good. Hey, I want some now.
which we've seen before. So because technically this one is better than the constant, right? This model has, you know, the better representative capability, right? Representation capability than the simple using W0. So that's why we reduce the training error for sure. But m equal 1 is not good enough. Let's use m equals 3. That you see here now it's better. Right, so that's where we further reduce the training and testing error by using this model, by using this regression model with power term, and the highest power term uses m equals 3, x to the power 3. Now.
Wait, what did he say? Man, I put it faster and then he goes faster.
By using this linear regression model with power term, and the highest power term uses m equals 3, x to the power 3.
So the highest polynomial power we use is m equals 3. I don't know if he means that in this example or like overall, but it just irked me when I saw it in the chat. It just irked me. Oh, okay. I'm using my flashing lights math. Nice. The highest power we go. So m equals 3.
Now, if we keep increasing, right, we see that when we increase m, we get better and better. However, suppose we keep increasing when m equal 9. That means now the linear model we use is w0, w1, oh sorry, x w1x, w2x squared, and 2w9x to the power square, to the power 9. So this is the model we use. But now you see what? So we find that the training data sets. So here, remember, we have two data sets. One is for training, but we also have another data set for testing. The data set in the training that will participate in the training loop help us to update with the testing, but not testing is separate. And then we will not use this testing data set to train model. Only when we build model, we use the testing to check performance. Right? So that's
Okay. Too many powers makes it inaccurate though. Like m equals 9 looks like this. So we have the same dots like that, but then it goes like that. It goes like all over the place. Do you mind if I eat it? The sky looks so beautiful. I can't find anything. Like what? Um, that's nice. The sky looks beautiful. I mean, the skies here look really cloudy, so it's not. I guess that's beautiful too. It's like not too gloomy. It's nice. I went outside to the farmer's market with my sister this morning. It's really good. Math? Yeah, I don't mind. Go for it. Less worry for me. So data sets we use for actually training data sets are for training the model. Training is for training. And then testing is for only for building. So we don't go haywire like the m equals 9.
why here, but now you see here the training will be really, the error will be really slow, will be really small, but the testing will be really high. So now let's see why. So if you look at,
So the more you train it, because the training is like this, the error goes lower, but the testing error goes higher. The training, oh, only the testing goes higher. Okay. So as the testing error increases, the training error decreases. Or
what the curve, it is when m equals 9, so if you look at the right line, a right curve, so this is what the model will learn. Actually, they pass through each training data point, perfect. Each training, so that's why we have this really low training error. But now suppose we have, some, suppose here we have some testing data items. So those are the testing data items. But now if you check the error, we might find that they are still high, right? They're still high. So that's why if there's an error, so that's why the testing will be still, the testing data set, the error will be still high. So that's why, this is the operation when we see when a model suppose m equal 9 is high value in this linear regression model, we will get a really small training error, but we have a really, high error on the testing data set. So that means what? When you use training data sets to train the model, you get a really low performance and you're happy with, and now if you use it in application, you will find they perform really high. Of course, this is the things we don't want because it's no longer satisfying, as we mentioned, the generalization. Right?
I can't type it.
Model, what we care about is performance on the new datasets.
Oh, he said something important.
Each training, so that's why we have this really low training error. But now suppose we have, some, suppose here we have those some testing data items. So those are the testing data items. But now if you check the error, you may find that they are still high, right? They're still high. So that's why there's an error. So that's why the testing will be still, the testing data set, the error will be still high. So that's why, this is the operation when we see when a model suppose n equal 9, this high value in this linear regression model, we will get a really small training error, but we have a really, high error on the
Won't be met if m is too high, even if what's it called, error is low. We want to test the predictability of new data sets.
Testing data set. So that means what? When you use training data sets, train the model, you get a really low performance and you are happy with. But now if you use it in application, you will find it perform really bad. Right? Of course, this is the things we don't want because it's no longer satisfy, as we mentioned, the generalization. Right? The model, what we check, we care about its performance on the new data sets. Right? Think about when you build a machine learning model, when you apply it and then you release it in the product. Of course, you want it have a good capability of handling the new data set. So generalization is the key things we care in the training, in the machine learning. Training data set help us to train a model. But testing data set is key the part we look at.
So testing is the key part we look at to check the performance. To check linear models performance.
To check performance. Okay, so now, so we observe, this, many different cases along by using different complexity level of the machine learning model. So now actually we can give some definition here. So at the beginning, suppose you choose a model very simple, which too simple to fit the data. We call this is underfitting. The observation you can get is the training error and the testing error.
This is called underfitting.
Both high. When the training error and the testing error both high, usually this is underfitting. The model too simple.
Testing error and training error.
Another case on the rightmost. So suppose you get a very complicated model. This model for sure can, suppose feed the data well, the training data set well, but when they perform on the testing, they will have a really low, a really high error. So we have a small training error, but a testing error. The error on the testing data set is really high. So
Okay, so let's see. Testing and training. Error.
this is what we call overfitting.
So simple model, complex model, overfitting. So the overfit is the testing data that perform badly. So the errors increase, and then the training has way lower error.
This is overfitting issue. So now, what is overfitting, as mentioned? So when you have a really complicated model, it performs really well on the training data set, but it performs really bad on testing. Whenever you observe this case, this is overfitting. Why? Because the model is too complicated. And this, we this model, because we only use training data set to train, so this model kind of like abuse.
You are a nerd because even I don't know this. How old are you, Kobe? Because you're a teacher, right? Yeah, I don't know this myself either. I'm just trying to learn it. This is machine learning. It's not learning about machines, it's the machine learning how to be a better machine. And that's what a linear model is. So, yeah, it's just a summer class. 40? You're 40? That's crazy. That means you could retire, right? I don't know. That's cool though. That's good. I did. Oh, you did retire. No way. So, yeah, how's the retired life, bro? I yearn for that. I didn't even have a job yet. Did you like your job though? Oh, actually, you said that you were gonna quit, huh? Indeed. And I teach coding. Cool. Wait, so don't coders have to know about machine learning? What's your major? Yo, Nasif, I think you're Muslim, right? Assalamu alaikum if you are. My major is applied math, statistics, and minoring in data science. This is the data science part. Major. Oh yeah.
Make the training data set happy, but it may have a really high fluctuation, right? To generalize the model or to represent the real structure behind the thing, because the training data sets, they're just the samples, right? Make those samples happy, maybe not good enough to.
Training is just simple. Training or testing, do you say?
To to represent the real structure behind the thing, because the training data sets, they're just the samples, right? Make those samples happy, maybe not good enough to make all the cases happy.
So training is just a sample. But won't always work with every data set, which is required for generalization. So we need both testing and training error to be low. That's the best. The best the best model has low error on both. I'm old. Nah, you're not old. 40 is young. You still have your energy. You have your money. You could enjoy your money. You could do anything. My dad is 50, turning 60. I think he's turning 60. I don't know where there was an applied math major. Cool. I didn't know there was. Okay. Yeah. I didn't know either. I didn't pick it. My sister picked it for me. I'm actually really dependent. I didn't choose my path. The path chose me. I'm super tired. It's fine. Just go to sleep. You'll be okay. Inshallah. If you, because 40 is really young, bro. Like you could be tired, but you could get it back. Yeah. Once you're 60, chances of getting it back are not that high. You could just like work out, quit your coffee, and then you'll feel better. I think.
So that's why, what we are looking for, actually, we are looking for here. So we are looking for a model that can have, can have a really good performance on the new data set. This is the key things we look at. When you select the model, suppose you train multiple different models, because here which we're gonna use, actually we will use some models from here. Right? For example, this one is the best. Why this one has a smallest, among the different models we train, this model has the smallest testing person.
I give my kids code money. Monkey? What is code monkey? Oops, sorry. I was trying to see it. It's like automatically hit it.
Right?
Alright, one. Wait, you have kids? That's cool. I mean, that's expected at that age, but um, yeah. I mean, at that point in life, you kind of achieved everything that you wanted, right? Have you traveled to anywhere like Spain or something? I kind of want to go to Spain. I don't know why.
One observation we find that, so here we wanted to know that, so when we train, when the overfitting comes, especially in this model, people figured out, for example, when m equal 9, so when you use this model, so here, this each row, shows the values of each parameter that we have in this model, W0 to suppose W9, okay, W0 to W9. When you use this very complicated model and get overfitting, you will find that those width value are getting really large. Okay.
Okay, so when it overfits, when a model overfits, the weight values jump really high. Japan. I look it up. Japan. Wait, what is Japan? I need to play my fist. What is fist, bro? What is, I don't know anything. Oh, is that Roblox? That's funny. It's funny how Roblox is just like it doesn't have a specific age range. Like anybody can play it. I need my Roblox. You could play with your kids. Why didn't you explore and search for a major you love, not your sister? I did. I chose animal science, but she made me change it because, and I'm grateful that I changed it just because like I wanted to be a vet, but vets don't get paid as much as they spend, and she struggles with loans, and that's like a huge problem. Like you do not want loans that you are not sure if you could pay off or not. That's gonna ruin your life. She doesn't want me to fall in that life wrecking situation that she's in. So she chose like the best high paying job, like the best career path for me, instead of just passion, money over passion. So I'm okay with it. There's going to coder when I die. There's going to coder, no coders. I think so. Cause actually I don't know. I don't know what you mean. Here's my cat. His name is Yuki. So Kobe, you are Japanese?
So this is one observation we find when overfitting happens. The reeds are get really large. So people think about if the reeds is too large, can we make it small? When once we get a model, we hope the reeds get small. Why? Because, for example, here, the larger the reeds value.
The weights are becoming huge to compensate for the noise. A small noise on X will have much fluctuation on prediction Y. Okay, so the smaller the noise, the heavier the weights, I guess. Half. Okay, so you're half Japanese. That's so cool. What is the other half? The other guy, Nick, is half Korean, half Russian. So it's cool. We have two of those here. Higher the smaller the noise, higher the weights.
It has the more chance it will have overfitting. Why? Because, for example, let's say here, suppose you have so this one is really good on this training data set, this complicated model. Suppose now we have the small changes. So this on the X, small changes on the X, because the weights get really large, so you will have a really large error. You know, you will have a really large error on the prediction. Why? Because the weights are large. So that's why we don't like the machine learning model with a large weight value. Large weight value cause overfitting, cause the big
السلام
error.
عليكم ورحمة الله وبركاته. Yo, Haya, wa alaikum assalam wa rahmatullahi wa barakatuh. Welcome back to the stream. How's it going? Holy, what am I looking at? This or this? This is, we're looking at different weights when the M equals a higher number and the M is like the higher power of the polynomial linear model that we're using to fit the data points the best. And testing out this higher number, we get higher weights, and the higher weights give us higher error, multiplying by the small noise, which is not what we want. We want lower weights, and that happens the lower power we get. Well, I'm not ethnically Russian, but I'm a Russian Korean. Oh, you're still here, nice. But ethnically Russian, oh, you mean like ethnically Mongolian, right? كيف حالك يا أختي؟ الحمد لله أنا بخير. وكيف أنت يا حياة؟ How's it going?
The prediction, makes the prediction not reliable. So the smaller the risk value, the more stable the machine learning model will be. So that's why how can we overcome?
So overcoming overfitting. How to overcome overfitting? Possible solutions. One workaround is use more data. And less weights, to make less weights, I guess.
Or reduce the overfitting issue. Here, one solution is using regression. Of course, another simple solution is using the more data. So, for example, here you use this small number of data sets as a training. Maybe they're not forced machine learning, to reduce overfitting by So, but if you use more data, like this may push the machine learning model, trying to make it better. So one is to increase the data sets that we have in the training data set. So this may help to reduce the overfitting, but more general theoretic.
Yeah, half Siberian, half Korean I prefer. Okay, okay, Siberian. You know, Siberian Huskies are so cute. And Siberian Tigers. So you're doing your homework? Yeah, I'm just taking notes of these lectures. I have a lot of assignments due tomorrow, which I hope I don't forget. Because it's Sunday. But, yeah. Monday. Mondays and Fridays are the due dates I should really focus on. Try not to forget. How do you manage to stream and still study well? I don't know. I don't know. I just like I'm paying attention to everything. But I think the stream helps me keep my attention span there. Otherwise, if I keep doing the stream like studying continuously, I'm gonna zone out. I'm gonna not pay attention. Only when the chat is like kind of inactive, I'm like looking back. So the other part, and also like talking to the stream, like trying to explain it again to myself and to you guys, even if you guys don't understand, it helps as well to hone in the point that he's making. Brain, I just realized I might be teaching. You might be teaching? What does that mean? Um, but yeah, this is just watching lectures. I guess that counts as homework. So this is one solution is to use more data. Another solution is using regularization. And what was regularization? We wrote it down here. Is avoiding overfitting. So types of regression, 1D regularization. How to overcome overfitting? Avoid it in the first place. Wow. So that's redesign the loss function by introducing regularization term, which is lambda summation mi equals 1, the weight I squared. Ooh. And then add that to the loss function. Redesign not loose loss function by introducing the regularization term. We're bringing you. I'm teaching you. Yeah, you are. I've learned a lot so far. I feel like, I don't know. Maybe you're just really smart, Julia. I don't know. I don't think so. Maybe it just clicks now and then later on I forget because I wrote a lot of notes, but I don't know. I still use AI. Hey, I'm smart too. You're smart. Yeah, you are. أشوفك على خير مع السلامة. مع السلامة. So you're gonna leave, Hayat? Only get the مع السلامة part.
Oh, yeah, of course, in practice, we also use this technique we call the regularization. Very, very important. Almost, especially in machine learning deep learning, people talking about the regularization. So you need to know what a regularization it is. So regularization is saying that in the loss function, okay, we redesign it by introducing a regularization term. So this is an additional term. So actually here, this is a regularization term. Previously, if you look at this one, this is what we call the MSE. And now the loss function, we revise it using additional term. And this is the sum of the squares of the weights, except W0.
Sum of the squares of the weights except what is not considered here? Oh, the weights. I don't know if that part is important. You take care. نعم سأرحل. I don't know what that means. I just know what نعم means, yes. But yeah, see you later, Hayat. Thanks for stopping by. He speaks English. Yeah, I'm sliming you. Alright, bro.
additional term. So actually here, this is a regularization term. Previously, if you look at this one, this is what we call the MSE.
So let's just rewrite the loss function. It helps tone it down as well. 1 over 2n, which is the optional part, I remember that. This is n, n. I equals 1, t I minus y. You don't really talk like a 40-year-old. I think you talk like you're younger. How does that feel? Do you feel your age? Do you feel younger than you are 40? I feel that about my age too. Like, I don't feel my age. I feel kind of embarrassed about my age, actually. Like, I'm not acting it. So, I would want people to assume that I'm younger so that I have more forgiveness, basically. For more room for mistakes. The expectation's not too high. I do feel younger. I see.
And now the loss function, we revise it using additional term. And this is the sum of the squares of the weights, except
some of the squares of the weights.
W0. So W0 is not considered here. So this is the regularization term. Okay. Why we have here? Remember, we want to do is we want to minimize. We want to figure out the width. The minimize loss function. The less the loss value it is, the better the model it is, right? So we want to minimize it. So this is the things we push the model
to minimize loss.
And then from the data,
just be you, but I don't act like one because you don't need to act like one. So you don't need to act younger. Just be you. Okay. Yeah, I don't try to act younger. I get embarrassed to say my age. Like, people, like, commonly, they don't like to say their age because they want to look younger. Like, by their face, to look prettier, I guess. But I don't mind that part. I don't mind looking older or whatever. I'm just, like, worried about people thinking, that I'm not mature. I wanna be mature, I guess. But, like, I'm kind of immature. Like, people younger than me are so much better with their age. Like, they act more their age. So, yeah, that's kind of annoying, right? Because people, when they don't act their age, like, it annoys people. It's like, why don't you act your age? Like, some things are not meant for you anymore. But I'm just, in my brain, I'm so much younger. I don't know why. I think it's lack of experiences.
Is the loss function. When we add this regularization term, so if you see here, because our goal is minimize this one, when we have this term, so we will push the model get a small width value, right? If you think about here, suppose you have a larger width value, this loss function will be large. Of course, when we use gradient descent want to minimize this one. When we minimize this one, it's kind of like we have this technique to push getting small width value. Why we want small width value again? What in the overfitting, we observe the large width value. Large width value tends to get overfitting issue in machine learning model. So that's why we want the small width value. Okay. So the regularization term is pushing the model to learn small width value.
Regularization pushes the model to learn smaller weight values. I'm 18. I'd like to look older, but I think it's just an Asian thing. To look older? I thought Asians want to look younger. Like the whole skincare thing in Korea is like crazy, and also in China especially. I know that's like not the same thing obviously, but Asian is Asian, right? I don't mean that racist. I'm saying like Asian. Okay, anyways, Chinese people they like rounder and bigger ears because it makes it look more youthful.
to feed the data. So this
That's
is a
like part of the beauty standard there.
recommendation term. Um, so as you may notice that here, okay, so probably let's look at this overfitting regularization term. And here this is just parameter. We want.
So the loss, the lambda is just like a parameter we want to specify. One way of dealing with this is to encourage the weights to be small, which is called regularization. Yeah. When the weights are small, prediction y will not be sensitive to small change of x. Smooth functions are preferred. When the weights are small, the prediction y will not be sensitive. Okay. Which makes y prediction y less sensitive. Yeah, I got you. Nice. Smooth functions are preferred. So one way of dealing with this, okay, so standard approach, new loss function. The penalty of the on the squared weights is known as ridge regression. Statistics. Penalty. Okay. So this is the parameter we want to specify. So, what's it called? Kobe, since you're half Japanese, what is the other half?
Specified because here when we have those two terms, this lambda is just just want to give kind of like the weight or the importance of this regularization term in the loss function. Okay. So for here, you may notice that for the lambda, when we specify the different value, the same MSE used, but just different lambda value. For example, when the lambda has this one, you can, even though when you use m equal 9, so you will get good or better in your model than fit data. Okay? So because when you specify this value, so for example here, so this will try to getting the small base value because we have this penalty term, right, or regularization term in the loss function.
This is the penalty term? The lambda?
For here, when you have this one, this means lambda, then lambda, log lambda to the negative 0 means this one is almost close to 0, right? So when this one suppose you set to 0, that means there's no regularization. Okay. But of course you don't want to specify this lambda really high, really large. If this one is really large, so this MSE will be it's kind of like will have a very, very tiny effect on the norm.
I meant by Asian thing that I look younger and don't really look that mature. Oh yeah. Asian genes they make you look younger. That's so true. And black genes, like black don't crack, and like yeah, Asians in general. We are doing homework. Yeah, Takoian Nasan Tokoian. Welcome to the stream. And yeah, we're doing homework. We're also yapping on the side so we stay more concentrated on the homework. Otherwise, we're just gonna get bored and not do it. And we're actually halfway done with the lecture. Actually, more than halfway. That's good. We have 20, 18, 19 minutes left. But we also have another one. So we have a lot of streaming material here. And these are all due tomorrow. This is due July 27th. class exercises. Suppose we have the following equations. Please draw the corresponding computational graph based on the computational graph you built and derive the formula of the derivatives of z with respect to x via backward pass. What in the world? And I watch all the lectures, guys. I'm not making this up. But let's not overwhelm ourselves. Let's just keep doing what we're doing. Just homework.
Loss function. It's kind of like the loss function will be purely have this point when lambda is huge. For example, when lambda equal lambda, this one is a really, lambda is huge, so this will force the model to learn the the curve like this one. Of course, this is what we want. So that's why the lambda should be properly selected the value. So another key things here why.
But lambda is the penalty on the squared weights. I'll write that anyway. Penalty on the squared weights is known as ridge regression.
So that's why.
What is your average grade in school? I feel like you're actually really smart. It's not that high, honestly. Maybe I come up smart, but I'm not. But my friend told me not to talk down about myself. It's hard not to. Like, seriously, I want to be honest, but he said to, like, yeah, be confident. Not being able to take compliments is a sign of low self-esteem. But to work on that, you have to just go against that. You have to unlearn that.
So another key things here why W0 we don't want. Okay. So here the thing. Suppose we have.
Why W0 can be not considered in the regularization term. So it's of 0. So why? Because
W1, x1, W2, x2, x square. So why the regularization? You see regularization term starting from I equal 1, not starting from I equal 0. That means W0, it is not considered in the regularization term. Why? Because, for example, suppose you have this one, which is represented by this polynomial. You may notice that W1, W2 contribute to the complexity of this curve. W0 does not. So if you increase W0,
so W0 does not. What do you say? Something the curve.
W1, W2 contribute.
Okay, so W0 does not contribute to the curve. The complexity of the curve. You're 19, right? Oh, actually, I never said my age. I guess because I'm shy, I said that I don't want to seem like... I don't want to be... I don't want to say my age because, like, I don't think I act like it. Okay.
The complexity of this curve, W0 does not. So if you increase W0, it's just lifted up. In the 2D space, right? Just move it up when you increase W0. But it has no changes to the shape of this curve.
It just increases it up. This moves the shape higher on the y-axis.
When you lower the W0, it's just moving down this curve, right? So that's why W0 does not contribute to the complexity of the code, does not contribute to the shape of the code. Only other parameters do. So that's why we, in this regulation term, we don't consider packaging the whole, context. Okay, so now let's review the linear model. So given the linear model, we have this one, W, now we consider the regression term.
Okay, but when I first joined your stream, I thought you were around 17 to 18. I also don't think you act childish or anything. Thank you! I appreciate that. I just, yeah, I don't want to come off like, yeah, I don't know how to explain it though, because, I feel like people my age, they have life way more figured out, so I get kind of insecure. At least maybe when I do figure out life a bit more, and I hope I do, I don't know if I will, but when I do, inshallah, I get a job, and then I make my own money, and then I know how to do taxes and all these things, then maybe I'll be able to say my age and not be shy about it. I don't know if I'll ever not be shy about it though. I guess it's just, yeah. I want to unlearn all that shyness, all that shame that I have. But it's gonna take a lot of work. I don't know how to even do that work. Hello, hi Guilty. Welcome back to this video. How's it going? Yeah, we're 101 minutes into the live stream.
We want to minimize the loss function. How to minimize it? Still going through the gradient descent. You compute the gradient of this loss function with respect to W. Actually, on the right, we show you the formula. Okay. So this is what we have, and then we consider, the regression term. So that's why the formula, the closed form of this derivative is are different from the previously because of regression term. What?
So this is the gradient descent of the loss function with the regularization. I don't know if I should be writing this down, how the gradient descent looks like. I'm doing good? Awesome. Yeah, I understand that you feel like you look too young and inexperienced compared to people your age. Exactly. It's not good to compare yourself. Everyone's on their own journey, of course. But when you say your age, people have an expectation. They're like, oh, you should be doing this or that. I don't know. I'm doing what I should be doing, yeah, but I should be better. I don't know. People, they say don't be shy about your age, but then they also have those expectations. It makes sense. You should have those expectations. They're there for your own benefit, but I don't really reach them for my own personal reasons. What you know about 6-7?
And we have this regression term, as mentioned. We consider this addition term in loss function. We want to minimize. We don't want to get. We want to minimize the loss function, but we don't want to get high weight value because high weight value may cause.
Initialize W randomly. So to minimize the loss, we want to initialize W randomly. Repeatedly update W based on the gradient, where E is the learning curve. So the gradient descent. So this is the gradient descent. Take the derivative of the loss function, starting with WO, and we get negative gradient descent, so that you move lower to where there's less loss. And then keep going down until we reach this till M. Okay, So that's the loss function all the way to m. I don't know if I should write the whole thing or the things in between. Anyways, so again, the gradient descent steps 1, initialize 0. I mean w0 or w, not w0. Random, picking a random by picking a random point, and then repeatedly update based on the gradient. And then that looks like this. W1 equals W minus the learning curve, well, times the gradient. Bro, I'm on to you, Nick. What did he say? You're dodging the question, Nick. He doesn't know what 6, 7 is. I just put those random numbers beside Nick was already taken. Oh, 5, 6, 7. I didn't see that.
Fitting issue in the machine part. Right? So this is what we have. Another thing we want you to pay attention because we use a regression term in the regression. So here there are some different models in linear regression model. For example, if the loss function you consider just MSE, okay, no regression term. This is just the ordinary least squares problem in it.
Okay, so these are more regularization models. I think I'm gonna stop here just because we did like a lot so far. And I'll continue later. I'm gonna eat, pray, probably do some chores, and then like come back, inshallah. Alright, take care guys. Thanks for watching and staying for the whole time, and see you guys later.